Hi, welcome to part 2 of our lecture on chapters 16 and 18. In part 2 of this lecture, we will be looking at electric circuits and Ohm's law. So far in part 1 of the lecture, we looked at electric circuits, and the three main concepts of an electric circuit are that we have current flowing through the wire, we have a resistance that impedes the current that flows through, and we have a voltage source over here, usually a battery, that actually pushes the current. So our goal now is to come up with a relationship between these three quantities, between I, which is current, V, which is voltage, and R, which is resistance. And our result is called Ohm's law. So again, what we've learned so far in part 1 is that voltage increases the current. You can think of the voltage kind of like a pump here that's pumping the current around the circuit. So the current I is proportional to the voltage, meaning if we increase the voltage, we get more current. On the other hand, the resistance decreases the current. Remember that the resistance is resistance to the flow of current. So the higher the resistance is, the less current we have. So the current is actually inversely proportional to resistance. If R is made bigger, then 1 over R is smaller, so that's proportional to the current here. So we can combine these two results here. We say that the current I is proportional to the voltage, so we'll put the V on the top, and it's inversely proportional to the resistance, so put the R on the bottom. And so this I equals V over R, we usually rewrite this and this is what we call Ohm's law. V equals I times R. So let's make sure we're clear on how to interpret Ohm's law. What V means in Ohm's law is the voltage across the resistor. So here's, remember our circuit symbol for a resistance or a resistor is this zigzag line. A voltage is actually a voltage difference that could be, for example, measured across this resistance. And the voltage is usually created by a battery or a power supply. We'll see examples of this shortly. So V is the voltage across this resistor. I is the current that flows through the resistor. All right? Current, remember, is flowing through these wires and through the resistance. And then R, of course, is the resistance. So V equals IR, or Ohm's law, is the most basic, fundamental, and important law of electricity. And we'll be using it quite often in this lecture to help us analyze simple electric circuits. Let's go ahead and look at some examples using basic circuits and Ohm's law. So the question here is how much current flows in this circuit? So here's a circuit diagram. So we learned how to read this in the last part of this lecture. This is the circuit diagram for a battery. And we're told here that the battery is a 6-volt battery. Over here, we know that this is a resistance, and we're given that the resistance is 3 ohms. So the question is, how much current flows? Well, we know that the current flows in this direction, clockwise, because remember, it flows from the positive terminal, which is the long line, around through to the negative terminal, which is the short line. But the question is how much? So here's where we use Ohm's law. Since V is equal to IR, we need to solve for I. I is equal to V over R. V is 6 volts. R is 3 ohms. And as long as we're using volts and ohms, all we have to do is take 6 divided by 3, which is 2, and the units will be amps or amperes. So the answer is 2 amperes of current is flowing in the circuit. Look at this question here. What is the battery voltage in the circuit? So this one's a little different. Notice the circuit looks the same. We've got a battery here, we've got a resistance over here, but look what we're given. We're given that 5 amps of current is flowing in this circuit, and there's a 10 ohm resistance. We don't know what the voltage of the battery is, so we can use Ohm's law, V equals IR, where I is 5 amps, R is 10 ohms. 5 times 10 is 50, and since we're solving for a voltage here, our units will be volts. So it is a 50-volt battery. One more here. The question is, how much resistance does this circuit have? So again, we have a simple circuit here with a battery connected to a resistance. We know that the battery is 12 volts. We're given that the current here flowing is 3 amps, where we don't know what the resistance of this resistor is. So let's calculate that using Ohm's law. So V equals IR. This time we're going to solve for R. So the resistance R is equal to the voltage divided by the current. The voltage is 12 volts, that was given. The current is 3 amps, that was given. 12 divided by 3 is 4, and since we're solving for a resistance, the units is ohms. So this must be a 4 ohm resistor. The examples that we just did were the most simple and basic circuits that we can have, where there's only one resistor or resistance. Quite often in a circuit, there will be more than one resistor. And the first type of circuit we're going to consider is called a series circuit, when there are 2 or more resistances and they're all connected end to end like this. In other words, they're in series or in a serial fashion. So the question here in this example is how much current flows through each resistor. So, in other words, how much current is flowing through this resistor here, how much is flowing through this one, and how much through this one. And the question is the current through each resistor different? Well, the first thing we can do here, and notice also in this example, we're given the battery voltage is 24 volts, and we have a 2 ohm, a 4 ohm, and a 6 ohm resistance. Now, if we recall and think back about the water pipe analogy, the current through a circuit must be continuous, so the current is the same everywhere. In other words, this current through this resistance has to be the same as this one, which has to be the same as this one, because the same amount of current flows around and around this circuit or loop. So we can replace all these arrows with just a single arrow that represents the one current that flows through this loop. So that's our starting point. The next thing we can do is in order to deal with resistances in series like this, the simple rule is that to come up with the equivalent resistance of all of these 3 resistors, we simply add them together. So 2 plus 4 plus 6 is 12 ohms. So we have simplified this circuit here. Instead of showing it with 3 separate resistances, we have lumped them all together into one resistance of 12 ohms. So it's a pretty simple rule. For resistors in series, we simply add them together. So now we can figure out the current of this circuit because we have a 24-volt battery and we have a 12 ohm effective resistance here. So using Ohm's law, V equals IR, we can solve for I, which is equal to V over R. V is 24 volts. The R is 12 ohms. 24 divided by 12 is 2. So the amount of current that flows through this circuit here is 2 amps. We can learn something else about the so-called series circuit if we apply Ohm's law to each resistor separately. So in our circuit that we just analyzed, and by the way, this circuit here is exactly the same as I showed on the previous slide. It looks a little different because I put the 3 resistances, the 2 ohm, the 4 ohm, and the 6 ohm, I put them side by side here instead of one over here and one down here. But notice that they are connected identically to what was shown before. So this is the exact same circuit. It's just drawn a little differently. Now remember, we figured out that there's 2 amps of current flowing through all of these resistances. So let's apply Ohm's law to this first resistor here. So we're going to call this voltage across this resistance V1. So V1 is equal to I1 times R1. So I1, remember, is 2 amps because that current is going through all of these resistors. So we have I1 is 2 amps and R1, this resistance, is 2 ohms. So 2 times 2 gives us 4 volts. So in other words, this resistor here has 4 volts across it. Okay, it has another way of saying this is it has a voltage drop of 4 volts. Let's go on and do the same thing to the second resistance. So V2 equals I2 R2. Now we're talking about this guy here. So again, the current I2 is the same as the current I1 because the same current goes through all of these. So again, we have 2 amps. But this time our resistance, R2, is 4 ohms. So 2 times 4 gives us 8 volts. All right, so this resistor has twice as many volts across it as this one because it has twice the resistance. And finally, for V3 here, V3 equals I3 R3. And I3, again, is 2 amps because of that rule with the same current flows through all of these. And R3 is 6 ohms, so 2 times 6 is 12 volts. So let's go ahead and add these 3 voltages together as we go around this loop. So 4 plus 8 plus 12 is 24 volts. And this is not a coincidence. 24 volts is the same voltage that we see over here with the battery. All right, so this gives us a rule here. The sum of resistor voltages around a series circuit equals the battery voltage. And the reason for this is due to the conservation of energy principle. The energy added by the battery, which is, you can think of this 24 volts as adding energy, it has to equal the energy lost by the resistors due to heat dissipation. All right, so if we add up all of these voltages here, they will always equal the voltage on the battery here. So what we've done in the last several slides here is come up with a set of rules that allow us to solve any series circuit. The 4 rules are: the same current I flows through the entire circuit. That's rule number 1. The second rule: the total or effective resistance is just the sum of all the individual resistances. In other words, just add them all together. The third rule is that we can use Ohm's law. Now remember, Ohm's law is V equals IR, or it also can be written as I equals V over R if we want to solve for I, or R equals V over I if we want to solve for R. These are 3 different ways of stating Ohm's law. They're all the same law, just written differently. And we can apply these for each resistor in the circuit as needed. The fourth rule is the one we just showed on the last slide. The sum of the resistor voltages always add together to give us the battery voltage. So let's look at an example problem. This problem is a little more difficult than the ones we've seen before, but by using our rules, we can figure out the answer. So we're given this circuit here, and we're told that 3 amperes flows through the 4 ohm resistor in the circuit shown below. And we're also told that the voltage across R2, which is this guy here, is measured to be 18 volts. So here's everything we're given. We have a battery, but we don't know what the voltage is of the battery. We have a 4 ohm resistor here. We have 3 amps of current flowing here, and we have an unknown resistance here, R2, but we know that the voltage across R2 is equal to 18 volts. So let's go ahead and answer 5 questions, which will ultimately lead us to figure out what the voltage of the battery is and also how many ohms of resistance this resistor has here. So the first question says, how much current flows through R2? Well, we know that 3 amps flows through this resistor, so remember the rule is the same current flows all the way around the circuit. So we must have 3 amps going through R2 as well. So that's our answer there. What is the value of R2? Well, we know that 3 amps is flowing through. We know the voltage is 18 volts across this resistance. So we can use Ohm's law, R equals V over I, and solve it for this resistance. So V here, we're going to use this, 18 volts, all right? And then the current, I2, we found that up here is 3 ohms. So 18 divided by 3 is 6. So we have found that this resistance right here is 6 ohms. Question number 3. What is the voltage across the 4 ohm resistor? That's this resistor up here. Well, we can just use Ohm's law to figure that out. For this resistor, we know that V equals IR, and the current is 3 amps, and the resistance is 4 ohms. So, let's see, where am I? 3 times 4 equals 12 volts. So we have 12 volts across here. Question number 4, what is the total circuit resistance? Well, we know that this one is 4 ohms, and remember we figured out that R2 was 6 ohms right here. So 4 ohms plus 6 ohms is equal to 10 ohms. Finally, question number 5, determine the battery voltage. Well, there are actually 2 ways to do this. The first way is to use the rule that, remember, these voltages across the resistors have to add up to the battery voltage. We know that this voltage here is 18 volts that was given to us. We found out that in question number 3, the voltage across the 4 ohm resistor is 12 volts. So 12 here plus 18 here gives us our answer of 30 volts. Now there's another way to solve this one. We know that the total resistance is 10 ohms, right? This was 4 and we found this to be 6. So 10 ohms times, remember V equals IR, so I is 3 amps times 10 ohms, 3 times 10, also gives us 30 volts. So there's actually 2 ways to do the final problem there. Let's now turn to a second type of circuit, which is different than the series circuit. This is called a parallel circuit. Let's start by going back to just a simple circuit here, which is just a single 4 ohm resistance connected to a 12 volt battery. And we can figure out the current here using Ohm's law, I equals V over R. So we have 12 volts divided by 4 ohms is 3 amperes. So I've written the current up here with this arrow. Now the question is, if we take this circuit here, and if we add another resistance here, so we're adding more resistance here, what will happen to the current here? Now notice the way I've added this resistance. It's not connected in series with this resistance. They're in parallel. All right, this is a very different connection. Series is when they're connected end to end. Parallel, they're sort of side by side. So this is called a parallel circuit. Now the question is, how much current is going to flow through this part of the circuit up here? Is it going to be less, more, or the same? What do you think? Well, it turns out that the current flowing through here will be more, not less. You may have thought that there would be less current because we're adding more resistance, but because this is a parallel circuit, things are very different. So resistors in parallel, when we add resistance in parallel, it results in more current. Why? Because it creates another path for current to flow through. So let's go back to our water analogy. Remember we had a pump here, and that pump is pumping water around this circuit here of tubing or pipes. Well, the resistance here is where the tubing gets really narrow. You can think of this like a little straw, like a drinking straw, where it's hard to force the water through there. So this kind of limits how much current can flow, how much water can flow. Well, if we add another resistance or another straw over here in parallel, notice we get twice as much flow now, because we can get flow going through this branch, or we can get flow through this branch or path. So we've added more paths by adding resistances in parallel. So the parallel circuit has less resistance than if there were just one resistance present. A nice way to sort of understand and visualize how parallel circuits work is the supermarket analogy. So imagine you go to the store, and let's say you go to Target, and there's a long line of people like this, all right? And the reason there's a long line of customers is because there's only one cashier working the register here. So all of these customers, this represents our current of customers, our flow of customers through the store. They're limited, obviously, by this resistance here. This cashier is what's slowing things down. So what would happen in the real world if this happened in the store? Well, they would open up another register. So now we've got two cashiers working in parallel. So the flow or line of customers can split. Half can go through this register, the other half can go through this register, and look what we've got now. We've got, remember, I is our current, which is the amount that can flow through one cash register. So here we have I, and here we have I going through this cash register, but these customers are all coming from one line back here, so the current through the store of customers is twice as much. We have twice the flow now of customers because we have twice as many paths or cash registers for them to flow through. So this is exactly what's happening in a parallel electric circuit. By putting another resistance in parallel, we create another path for current to flow, which gives us more overall current. Before we return to our parallel circuit and analyze it, there's another very important rule or law that will help us, and it's called conservation of current. So electric current, like water flowing through pipes, is conserved, meaning current can't be created or destroyed inside the wires. So what this means is that the current going into a junction must equal the current coming out of the junction. So what do we mean by a junction? Well, a junction is when two wires like this are connected together. So the current flowing through this path meets up with the current flowing through this path, and they combine to be the total output current. So this is the junction right here. So look at this picture here. Let's say we have 4 amps of current flowing through this path, and we have 3 amps of current flowing through this path. Well, since these two paths of currents combine, we know that the total current flowing out must be 7 amps. All right, so this is what we mean by conservation of current. So this is another basic, fundamental, and important law of electricity that we're going to use to help us solve some of these problems. So take a look at this little mini quiz problem here. Here, our input current, we're told, is 5 amps, and here's a junction, and we're told that this path up here has 3 amps of current. So what would be the current flowing through this path of the circuit? Go ahead and maybe pause the video and see if you can think of the right answer there. Well, the answer must be 2 amps flowing through this pathway, because we know that there's 5 here and we've got 3 here, so this must be 5 minus 3, which is 2 amps. In other words, this 3 amps plus this 2 amps give us the 5 amps that we're flowing into this junction. Let's now look at a couple more sort of conceptual problems that will help us understand how circuits work. So these are questions that have to do with current continuity, similar to what we just did on the last couple of slides. So in this first example here, it says, which way does current flow in the circuit? Now this symbol up here, this thing here, you can think of this like a battery. This is the positive terminal of the battery, and this is the negative terminal of the battery. All right, so which way is current going to flow through these wires? Is it going to flow in a clockwise direction like this, or is it going to flow in a counterclockwise direction like this? Well, the answer is clockwise, because remember, current always flows from positive to negative. Okay, now question B says a light bulb's brightness depends on how much current flows through it. So which light bulb will be brighter, bulb 1 or bulb 2? So again, what makes a bulb bright is how much current flows through the bulb. If more current flows through, the bulb is brighter. So pause the video and think about the brightness of these two bulbs and which one will be brighter. Well, the answer is sort of a trick question. It's neither. The bulb 1 and bulb 2 will have the exact same brightness. The reason for this is, remember, the same current flows through the whole circuit. So the same current that goes into bulb 2 must also flow through bulb 1 and then back through our battery. Okay, the next problem down here is a little trickier. So again, think of this as our battery up here. And now notice we've got 3 light bulbs, one here, bulb 2 here, and bulb 3 here. So again, the first question is, which way does current flow in this circuit? So go ahead and pause the video and look at that diagram and trace out which direction current's going to flow. All right, so current we know goes from the positive terminal to the negative. So the current is going to go from this positive terminal here through these bulbs and then through bulb 1, and it's going to return here to the negative terminal. Now, part B, rank the bulbs from brightest to dimmest. So go ahead and pause the video and see if you can figure out which of these bulbs, bulbs 1, 2, or 3, is brightest and which one is dimmest. Well, the answer is that bulb 1 will be brightest, bulb 2 and 3 will be tied and both be dim. Now, why is this? Well, you have to trace the direction of current. The current comes from the battery here, but then look what happens. It splits into 2 paths. Bulbs 2 and 3 are in parallel. So they only get half of the current each, which makes them dim. But then here's a junction. The current recombines here, and we have twice the current going through bulb 1, which makes it brighter. So that's why bulb 1 is the brightest of the 3. So let's use some of the tricks that we just learned to analyze a parallel circuit. So the current, if we think of, here's our parallel circuit down here. We've got a battery, and we've got 3 resistances in this one, all connected in parallel to each other, okay? So the first rule here is that the current through the battery is the sum of currents flowing through the parallel resistors. So what does that mean? Well, it means that this current here, which we'll call I total, the total amount of current flowing through this battery and through this path here, has to split. Some of it goes down here, I1, some of it goes down this path, I2, and the rest goes down path I3. So I total, this current right here, must be equal to I1 plus I2 plus I3. This is just the current continuity law that we just talked about in the last couple of slides. The next thing we can do is let's figure out the total current in this example. So we've got a 12-volt battery, and we've got a 2 ohm, a 4 ohm, and a 6 ohm resistance all in parallel here. So let's apply Ohm's law to each resistor individually. So we're going to actually calculate the current here. All right, now the first thing that we see here is that we're going to solve for current. So I is equal to V over R. The question is, what is the voltage across this resistance here? Well, if we trace back the wires, notice they're connected directly to the battery. So the voltage across this resistance is 12 volts. So the current is 12 volts divided by its resistance, 2 ohms, which is 6 amps. So I1 is equal to 6 amps. Let's now do the same for I2, this resistance. So I2 is V2 over R2. Now the question is, what is the voltage across this resistance? Well, here's the trick. For a parallel circuit, I can trace back directly here to the battery. Notice I can go down here and trace directly back without going through any other resistances. That means that this resistance also sees 12 volts across it. So this is, I think I may have forgotten to mention this on the previous slide, is that in a parallel circuit, all of the resistances see the same voltage, which is the voltage of the battery. So for this current here, we have 12 volts divided by 4 ohms, right? This is the 4 ohm resistance. 12 over 4 is 3. So I have 3 amps going down this leg of the circuit, or this path. Finally, for this one here, again, the voltage across this resistor is 12 volts because I can trace all the way back directly to the battery, and it's a 12-volt battery. So I have 12 volts this time divided by 6 ohms. 12 divided by 6 is 2. So we have 2 amps going through this path of the circuit. Now, the total current here is, remember, the sum of I1, I2, and I3. So I have 6 plus 3 plus 2 is 11 amps is my total current. Now, the equivalent circuit here, if we want to try to lump all of these resistances together into a single resistance, we don't know what that value would be. Now, this is not a series circuit, so we can't add them together, all right? But what we can do is use what we know. We've got 12 volts. We know we have 11 amps flowing here, right? We just figured that out up here. And we can figure out what this R is. From Ohm's law, V equals IR, we have R equals V over I. So we have 12 volts divided by 11 amps. 12 divided by 11, you'll have to do that on your calculator, is 1.1 ohms. So we can summarize all this for parallel circuits and come up with 4 rules for parallel circuits. The first rule is the battery voltage appears across each resistor. So if you have a 12-volt battery, we have 12 volts across each resistor in a parallel circuit. Rule 2, the total current through the battery is the sum of the parallel resistor currents. So in other words, if there are 2 resistors, then the total current is I1 plus I2. Rule 3, the total or effective resistance is found by Ohm's law. Our total is equal to the voltage of the battery divided by the total current. And then, as always, we can use Ohm's law in either of its 3 forms for each resistor as needed. So let's go ahead and do an example. So here we have a circuit. So the first thing we can do is identify that this is indeed a parallel circuit. We've got 2 resistors here shown in parallel. They're connected to a 12-volt battery. We're told that there's 6 amps of current flowing through this path up here of the circuit. We don't know what this resistor is. It's just labeled R1. And we know that this one, R2, is equal to 6 ohms. So let's answer these questions. What's the voltage across R1? Well, that's easy. It's 12 volts because it's connected directly to the battery. What's the voltage across R2? Remember the rule. That's also simple because both of these resistances are both connected directly to the battery because they're in parallel. So it's also 12 volts. The current through R2, we know that I2 is equal to V2 over R2. So we have V2 is 12 volts divided by this resistance, 6 ohms, 12 over 6 is 2 amps. The current through R1, all right, well, we know that this current through here plus this current through here must be equal to 6 amps. In other words, I1 plus I2 is equal to 6. But we know that I2 is equal to 2 amps. So therefore, I1 must be 4 amps. 2 amps here, 4 amps here, total together to give us 6 amps. Finally, what is the resistance of this resistor here, the one that we weren't given any information on? Well, we know that R1 is equal to V1 over I1. So V1 again is 12, and we've determined that I1, the current through here, is 4 amps. So 12 divided by 4 is 3 ohms. Therefore, this is a 3 ohm resistance. The last topic of our chapter here on electricity is electrical power. So remember, we talked about power back in chapter 8 when we were learning about energy. Power is the work done or energy transferred per unit time. So power is equal to energy divided by time. Now we can do a little trick here to come up with this for electricity. So what we can do here is we have energy over time. So let's divide and multiply by coulombs. All right, so notice what I did here is I took coulombs and I put it on the bottom underneath energy, And I also took coulombs and put it on the top over time. So notice that these two coulombs cancel each other to give us energy over time. So this is a little trick. We've inserted coulomb twice, once on top, once on the bottom, without, this is allowed completely because they cancel each other. Why do we do this? Well, remember that energy per coulomb is the technical definition of a volt. And coulombs per time is our definition of current, which is I. So this leads to a very simple result. Electrical power, P, is given by the voltage multiplied by the current. And the units of electrical power, remember, are joules per second, which is called a watt, and that's abbreviated with a W. So let's look at an example here. A flashlight with a 9-volt battery draws 0.2 amps of current. What that means is that that's how much current is flowing in this circuit. How much power does the battery supply and how much power does the light bulb give off? So here's how we're going to model this flashlight. The flashlight has a 9-volt battery, and we're going to model the light bulb as a resistance, okay? Because that's what the bulb actually is. It's a skinny little wire that heats up and glows and gives off light and heat. So that's the resistance here. So we're told that the current is 0.2 amps, and if we want to, we could figure out the resistance here using Ohm's law. Remember, R is equal to V over I, so 9 divided by 0.2 is 45 ohms, okay? We actually won't need that, but notice we could figure that out for this light bulb. But let's talk about the power now. The battery, its job is to supply power to the circuit. How much power does it supply? V times I. Remember, P equals VI. So we have 9 volts times 0.2 amps is 1.8 watts of power. Now the bulb dissipates power. In other words, the battery supplies the power. Where does that power go? Well, it actually gets converted into light and heat, which leaves the circuit and goes into the environment. So how much power does the bulb dissipate? Well, we use the same thing. P equals V times I. Notice the bulb is connected to the 9-volt battery, and the current flowing through the bulb is, again, 0.2 amps. So not surprisingly, we get the same number here, 1.8 watts. In other words, every second, 1.8 joules is dissipated by the bulb. Where does that energy come from? It comes from the battery. So this is nothing more than the conservation of energy. The amount of energy that the battery supplies is the amount of energy that the resistance here dissipates as light and heat. Here's our last example for the chapter. Your electric hairdryer is rated at 1500 watts. How much energy do you use when you dry your hair in 3 minutes? So remember again, power is equal to energy divided by time. So let's solve this equation here for energy, because that's what we're asked to. How much energy do we use? So energy is equal to power times time. The power is 1500 watts. The time, remember, was given as 3 minutes, but we have to convert this to seconds, okay? So a watt, by the way, remember, is joules per second. So this 1500 watts, I'm going to change that to 1500 joules per second. And 3 minutes, remember, of course, a minute is 60 seconds. So 3 minutes, we have to convert that to seconds. That's 180 seconds. So our answer is 1,500 times 180. And this is, surprisingly, a lot of energy. It's 270,000 joules just to dry your hair in 3 minutes. Notice here again, the seconds canceled here, and we're left with just the joules. So just a reminder here, what's happening with your hair dryer is electrical energy is being converted into heat or thermal energy. And obviously, when we use something like a hair dryer, we're using up a lot of energy because we're generating a lot of heat during that process. So that, my friends, is chapters 16 and 18. Our topic was electricity. We are done with this, and I will see you for our next topic soon. Goodbye.